When we say power series, we mean powers of x. Wow, those are wild.
Oh my goodness.
Yeah, those are wild.
Really cool.
Let's see. Other things that came up on here. There was also a very common mistake which threw me off a little bit, was right here. So on 11, and the part that threw me off, I was a little surprised at, is that when we are doing the ratio test, if you did the root test is way harder on this problem than the ratio test. The root test only works really cleanly if you have a power on the far outside. So if you don't, the root test gets very sort of finicky here because you'd be doing the kth root of 3 limit, the kth root of the denominator limit. So that's sort of a more complicated approach if you were going to go root test. You can do it, but it's much more complicated. But the part that was throwing me off, there was a handful of you that didn't cancel these 3's and left a 3 in there. When you have your a sub k plus 1, bless you, a sub k plus 1 right here, and you divide by a sub k, so you flip a sub k, those 3's cancel with the ratio test. So there was actually not an insignificant number of you that didn't cancel the 3's, and I couldn't figure out why. If you approached it with the root test, I could see how you made a mistake. And if you did approach it with the ratio test, with the root test, can someone tell us what this limit is? The kth root of 3 as k goes to infinity? So if you were going to do the root test, obviously the kth root of x to the k is x absolute value of x. But the kth root of 3 as k goes to infinity, does anyone know? If you had to figure it out, what would you use? What technique would you use? Double L? Log limit? Log limit? Right? You would do the log limit process like we've been doing. We'd say, okay, let's like k equal, or y equal the kth root, or the xth root if we wanted to switch to x's, which I will do because x's and y's seem to go better than k's and y's. So if we were doing that, and then what would we do to both sides?
Natural.
Yes, this is 3 to the 1 over x, so we want to pop that exponent down, so we would take the natural log of both sides, and we would have 1x times the natural log of 3. And then we would take the limit of both sides, we set up a L'Hopital's rule, we take the derivative, blah, 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 and in the end you get that this limit is 1. So in class I showed you, we worked out the kth root of k has a limit of 1. Also, the kth root of this number, any number, will have a limit of 1. So that's why if you tried the root test, you got tangled up, because nobody got that correct if you took the kth root of 3. No one got that limit right. But to do it, you would use the log limit process. So that happened. There was some... Oh, another interesting algebraic mistake I saw was on the one where we're centered at 4. So I think it was before this one. Centered at 4 is 10 or 11. When you take the absolute value of x minus 4 raised to the k power, again, not an insignificant number of you wrote this as the absolute value of x minus 4 to the k. That is not true. That is not true. The absolute value of this entire expression here, you can push it inside the k, but you can't then, distribute the absolute value symbol. This has to stay wrapped around the x minus 4. If you did this thing, then you got the wrong interval of convergence, the wrong ratio, the wrong radius of convergence. Everything went sideways. So if you're taking the absolute value of a quantity here, the absolute value does not distribute. Doesn't distribute. Just like a square root doesn't distribute. If you have the square root of x minus 4, you can't make it the square root of x minus the square root of 4. Functions generally don't distribute. Let's see, was there anything else that was crazy weird? No, there's nothing. That stuff down at the end was pretty decent. Some of you wrote the arctangent function fine. Many of you didn't. Some of you didn't put the x. Some of you put a 1 plus x. Some of you didn't alternate it. So there's all sorts of little mistakes. But make sure you integrate next. There's at least 2 of you that just didn't integrate. So once you have your, and you're dealing with a series, you should have the plus dot dot dot. We're integrating a series. We're not integrating a polynomial. We're integrating a series, so you should have the dots. And then your result is an alternating series. So if we're trying to do an approximation, the only approximation that we've dealt with in this class with any detail is for an alternating series. There should have been a little bell going off in your head if you ended up with everything plus. We don't have a way to approximate that we've handled in this class. The only approximation that we've spent any time on is the alternating series approximation, where you have to have an alternating series, and then the value of the third term approximates the sum of the first 2. The value of the fourth term approximates the value of the first 3. So if this is not alternating, ideally a bell should have gone off, because the only way we have been dealing with approximations is if the signs are alternating. So make sure that that sort of makes sense to you before the final exam, which is a week from Thursday, somehow. The first problem was geometric series. And there was all sorts of funny, not all sorts, but I saw a few things that were interesting. When we're talking about a geometric series, like, it didn't say that you had to use the geometric series principles. But if you use something like the ratio test or some other test, you might be able to say conclusively that it converges. But the only way you're going to be able to find the sum of a geometric series is by setting it up in the geometric series format, where you identify R, you identify A, and you use that formula, A divided by 1 minus R. That's the only way you're going to get to the actual sum of that series. So make sure on this first one, because that's a super common one, that you understand those laws of exponents and how to manipulate the powers. With a geometric series, we want the power to be just k. And so look at your mistakes on that. Look at the key and make sure you understand that kind of thing. Okay, those are the main ideas. So take a look at the exam, look at my comments, make sure I added the points up and divided by 15 properly. And then if you look at the key and you're not quite sure, let me know, and we can go over anything that you're not clear on. Before the final, next Thursday, a week from Thursday. That is so exciting. That means summer's here. Very close. All right, so let's take a look. The high A on this one, I think, was 95. There were 4 A's. I forgot to write down the summary of the test, but the average was 69 and the median was 72. Generally, median is a more important number when we're looking at exams these days, because that is quite a range of scores. So averages can be skewed by like a 10% versus, you get the idea. So medians are generally more kind of give you a better sense of what's going on. All right, let's go to chapter 12, our final chapter. We're only doing 3 sections in chapter 12. And chapter 12 is, I would say it's the easiest chapter we're going to cover. It doesn't mean that you don't need to grind the last 2 weeks of the semester. There is work to be done, but conceptually it's a much easier lift than these power series or some of the other topics that we've done in the semester. So let me ask you a basic question first. what is the equation of a line? Let's say a line in two-dimensional space. What is the equation of a line? When you just think of a line in two-dimensional space, what equation pops to your head?
X plus b.
Say again?
Mx plus b.
Mx, so y equals mx plus b. So that's the slope-intercept form of a line. And so we call that slope-intercept form. If you wanted the general equation of a line, generally you would write it as ax plus by equals c. So you put both the letters, the x and the y, on one side of the equation. Okay? So my question to you is, how about a line in three-dimensional space? Anyone know the equation of a line in three-dimensional space? If you had to guess, if someone said,
ax plus by plus cz equals d.
that is the absolute intuitive guess. And depending on the college algebra class that you took,
Is it polar coordinates?
no, we're not going to, no, in rectangular.
Okay.
So we're going to talk about it in polar today. So in rectangular, the simplest equation in two-dimensional space, ax plus by equals c, gives you a line. And I 100% agree that this is the simplest equation that you could generate in three-dimensional space. But is that a line? Anyone know what the graph of that is? It is actually not a line, but it is the simplest equation in three-dimensional space with rectangular coordinates.
Is it a plane?
It's a plane. It is a plane, and I'm going to write something down here that you will not be tested on until Calc 3, and you do not need to write down unless you're a grinder. This plane is sitting in three-dimensional space, and if you pluck off these three coefficients, a, b, and c, that's going to create a vector that's going to be perpendicular to the plane. It's going to be like a handle on the plane. So this is a plane in three-dimensional space. That vector is called the normal vector to it. It's a perpendicular vector to that plane. So it is not a line, though. And this is the motivation for the topic we are about to talk about, parametric equations. The obvious question is, well, why would we want another type of equation if we already have rectangular equations. We've been doing them our whole life. Why have a new type of equation? And the answer is because the simplest curve in three-dimensional space cannot be represented with a rectangular equation. If the simplest equation can't be represented with rectangular equations, we absolutely need another way of describing curves in three-dimensional space. So that's why we're going to go with this parametric equation idea. Parametric equations are going to be great for modeling paths. So if we're looking in two-dimensional space, we can create parametric equations. I'll show you what they look like in just a sec. Well, if I slide down a little, you'll see an example. So the idea is that with parametric equations, we define this third letter called the parameter. And we're going to have some equation of t for both the x and y. So we're going to build an equation for the x coordinate as a function of t, and we're going to build an equation for the y coordinate as a function of t. And one of the cool things about parametric equations is that you can track paths really easily. You can say, oh, let's suppose t equals 0 is right here, and you can sort of create this little timeline that tells you where the object is at a particular time value. So that immediately you can see why that could be helpful. Like if we're modeling a trajectory, we want t equals 0 to be the launch time. T equals 0 is when the rocket or the ball or whatever is in its static position, and then it launches, and as time goes by, we want to know exactly where it's at. Rectangular equations can be used to model paths in two-dimensional space, but not three-dimensional space. We have to have parametric equations to map a path in three-dimensional space. And so that's what we're going to do. That's why we're using these. And there will be, these parametric curves will have an orientation. And all the orientation means is the direction of increasing t. So we just imagine, these little arrows that are sort of mapping the path of the ball or the rocket or whatever it is. as t gets bigger, which direction is the object moving. So parametric equations have parametric curves have orientation. All right, so the question is, how do we graph a parametric curve? This is an example of a set of parametric equations. Parametric equations build a parametric graph, and the gist of it is right here. So we've got these parametric equations. We see x and y are now functions of t. You can't see t in the picture necessarily. So the way we are going to start graphing parametric equations, we don't have any intuition for what they look like yet. So we need to build some intuition for what a parametric graph looks like. So here's what we do. We're going to go back to rectangular when we're in two-dimensional space to start establishing a handle on these. So we're going to eliminate the parameter t. Often Pythagorean theorem, if we see trig functions, will be helpful. We're going to graph the Cartesian equation. You will usually graph it with dashes. And then we're going to apply the parametric domain. We see a domain on this parameter t. And then we're going to graph the parametric curve and indicate the orientation. So those are our steps. The bigger picture is that the parametric curve will always be a subset of the rectangular curve. It may be the entire rectangular curve, or it may be a portion of it. And what we're going to see with a parametric domain is that you can grab a piece of a circle really easily. You know, if you have x squared plus y squared equals r squared, it's very hard to grab the piece of the circle, say, from 45 degrees to 95 degrees. But with parametric equations, it's going to be very easy. So let's follow these steps. So eliminate the parameter. So the first thing that we see is that we're dealing with trig functions. And we know this fact about trig functions. We know that sine squared of t plus cosine squared of t is 1. So that's true for all t. So that's true. Well, let's just do some substitution here. We see that sine of t is y. So sine of t is y. This just translates to that equation, which is the unit circle. Normally, we write the equation for the unit circle in alphabetical order. It does not matter. And so that is the rectangular graph, or the rectangular equation, which corresponds to this rectangular graph, circle of radius 1 centered at the origin. So that's step one. So step one, we've eliminated the parameter t, and we've got a rectangular equation. So that's our first step. Get rid of t. We use the Pythagorean theorem to do it. Second step says graph the Cartesian equation with dashes. All right, there it is. That's a unit circle centered at the origin. Third step says apply the parametric domain by plugging in points. So generally what I recommend is doing a little table of values. So back to algebra stuff. And this domain is 0 to pi. So we definitely want those endpoints, but then we always want a point in between. We'll see why that becomes important later. The idea is that it's hard to know whether you're going clockwise or counterclockwise. If you only have 2 points on this circle, how are you getting between the points, clockwise or counterclockwise? So picking a point in between helps us. And now we go to our parametric equations right here. Let's figure out what x is when t is 0. So we plug in 0 here. Cosine of 0 is 1. Sine of 0 is 0. So this is where we are. This point is plotted when t is equal to 0. So that's our start point. Now pi over 2. We plug pi over 2 in here. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we're at 0, 1 when t is pi over 2. And we plug in pi, and of course we get negative 1, 0. So here's where we are when t is pi. And so this shows us that we're going around, and we don't put these arrows at the endpoints, we just sort of stick them in the middle. That's the orientation. So the parametric curve is this upper semicircle graphed counterclockwise. So counterclockwise is this way, clockwise is the other way. So that's the parametric curve. So it was super easy to get the top half of that semicircle. We didn't have to deal with any square roots. Normally, if you wanted the upper semicircle of a unit circle, you'd have to say, oh, y is equal to the positive square root of 1 minus x squared. Bit of a pain. This, as t goes from 0 to pi, you just plot the points nice and cleanly along the circle. The geometric interpretation of t in this case is obvious. What is t representing?
Theta?
It's representing the angle, right? Theta. Right? When t is 0, the angle is 0. When t is pi over 2, you've got a counterclockwise rotation of pi over 2. And so this is cool because the t, or the parameter, has a geometric value. We can see what the t is meaning. Many times the t value doesn't have this nice geometric value, but a lot of times it does. So it just kind of depends on the problem. All right, so this parametric curve is a subset of the rectangular curve. It's not the whole rectangular curve, the Cartesian curve. It's just a subset. And I think that was the question on there. All right, so let's take a look at this one. Oh, parametric equations will yield a parametric curve. To get to the parametric curve, we're going to get rid of the t first and then see what happens. Once again, we see trig functions. Whenever we see trig functions, we want to have we want to be at least considering the Pythagorean theorem. And the Pythagorean theorem is true no matter what angle you put in here, as long as it's the same angle for both these trig functions. So we could put in a minus t. It's true for any t. So if we replace t with minus t, it's still true. As long as these two angles match, that is true. And so, well, we end up with the same Cartesian equation. X squared plus y squared equals 1, which is the unit circle. So this Cartesian equation is identical to the last one. Same exact Cartesian equation, same exact dashed curve. All right, but now we do our table of values. So we're going to do our t, x, y. And let's figure out where we are and where we're going. And again, we want to use our endpoints for our interval, 0 to pi. And we want to pick a point in the middle somewhere so that we know which way we're going. If we have a closed Cartesian curve, 2 points isn't enough to dictate whether we're going clockwise or counterclockwise. We need 3 points to know exactly which direction we're going. OK, so we plug in 0. We come up here. We have cosine of 0 and sine of 0. Cosine of 0 is 1. Sine of 0 is 0. So once again, we are starting right here. So that is our start point. That's where we are when t is 0. And all of your graphing utilities can graph parametric curves. Desmos, all these things, they can all graph parametric curves. Pi over 2. Now we plug in pi over 2. We get cosine of negative pi over 2. That's 0. Sine of pi over 2. Plugging in pi over 2 here, we get sine of negative pi over 2. And what is sine of negative pi over 2? Negative 1. So we are down here when t is equal to pi over 2. And when we plug in pi, cosine of negative pi is negative 1. Sine of negative pi is 0. So we are here when t is equal to pi. Clearly, we are going this way. This is the direction of increasing t. And then we put our orientation arrows somewhere inside, not at the endpoints. So there's our parametric curve. So our parametric curve here is the lower semicircle with clockwise orientation. We're going clockwise. We're spinning to the right. So that's clockwise orientation. OK. Now, it is not always true that replacing t with negative t reverses the orientation. It's Like, there's a lot of times where you're dealing with parametric curves and you just have to fiddle if they say, oh, reverse the orientation. Sometimes replacing t with minus t will make it go clockwise instead of counterclockwise or vice versa, but not always. You have to just play with things. Here's another thing we can play with. The first curve we did was cosine sine. Now let's do sine cosine and see how that changes it up. So once again, our first step is that we see trig functions, and when we see trig functions in a parametric context, most often you should be jumping to the Pythagorean theorem. This is what allows us to eliminate t. You do not want to solve one of these. A lot of times when you have a system, you solve for the variable you're trying to eliminate and then plug it into the other one. You do not want to solve for t and say t is equal to the inverse sine of x and then plug it in down there. You don't want to do that. And we don't want any inverse functions in here. That just makes things way more complicated than we need to do, than we need to deal with. So then we're going to come over, build our table, figure out, okay, well, we've got our Cartesian curve. Our parametric curve is a subset. It might be the whole thing, but it could just be a proper subset. So we're going to plug in our endpoints for sure and grab a point in the middle for good measure, so you know if it's clockwise or counterclockwise. Plug in 0. Sine of 0, that's 0. Cosine of 0 is 1. So right away we see that we're starting somewhere different. That's where we start. T equals 0 is the North Pole here, all the way at the top. Plug in pi over 2, and we end up with x being sine of pi over 2, which is 1. Y is cosine of pi over 2, which is 0. So 1 comma 0. This is where we are when the angle, or the parameter, is pi over 2. And plugging in pi, sine of pi is 0, cosine of pi is -1. So 0, -1, right there. So here is our parametric curve. Subset of the Cartesian curve. Orientation is clockwise. So that's how we can grab a right semicircle. Just switch the coordinates. Normally a right semicircle, we would have to solve for x. X equals the square root of 1 minus y squared. Walter?
Does the other point that we choose to look for orientation necessarily have to be the midpoint, or can it be any point?
It can be any point in between. So if we would have picked pi over 4, we would have got that point there. We just need we need some third point so that we know that we're going this way and not this way.
Gotcha.
Yeah, usually I'd pick the middle one, but you don't have to. You're absolutely right. You can pick anything in between the two, will tell us. It just has to be in the domain here. So the parametric domain is, if the parametric domain is not given to us, what do you think this curve would be if the parametric domain was not given to us? So it's going to be the full circle, but it's going to be the full circle copied out an infinite number of times. Right? So as we're just spinning, we'd be spinning forever. So one thing that's very different with parametric curves is that you can graph on top of yourself. You can graph on top of the curve. You can do two loops, or 3 loops, or 4 loops, or whatever. Very different from a Cartesian curve, right? With Cartesian curves, we don't have that. That's not a thing. Like if we look at a Cartesian curve and we want to find the arc length, we know, just go from the first point to the last point. Whereas here, if we did the full circle, if we wanted to know what the perimeter of this circle was, the circumference, we need to make sure that that circle is being traced out one time and that there's not extra loops. So it's a little bit different from Cartesian in that way. Just looking at it's not enough. Like when you're looking at a Cartesian graph, you can tell where it's not differentiable. You can see that there's a cusp or a corner or a gap. With parametric, there's times where you could be graphing this way and then all of a sudden it reverses directions. So you have to be a little bit careful because there can be hidden points of non-differentiability. Normally with a Cartesian curve, if it looks smooth, if there's no corners or cusps, then it's differentiable. But a parametric curve, you got to be a little bit more careful because you could have these hidden cusps where the curve just starts turning around and going backwards on itself. So there's some slight differences. We have to be careful with our domains. All right, so that is that one. I don't know if this is going to work here. Desmos is really, yeah, that happened in my office too. But if you click up here, it should open Desmos right up. So Desmos is a great tool to get a handle on how some of these little tweaks will change your curve. So if we just do a couple fiddly things here. So right here, cosine sine, that's the first one we did, and we saw that, so we can see the orientation here, right? It's going counterclockwise. And 2 pi is going to give us 1 full circle. Here's the second one we did. This one also starts at 1, 0, but it's going to go clockwise. So that's when we replace t with negative t. So that, in this case, just changed the orientation, but the start point was the same. Here's the third one we did, where we started at the North Pole and went clockwise. And then for this one, I replaced t with pi minus t, just for the heck of it. And notice that it's going to start over here at the West Pole, and we're going to go clockwise. So there's all sorts of things that you can fiddle with to change the orientation or to change the start point. And it's not always intuitive. You just have to go through the process that we went through, where you build a little table and you figure out where you are. Yeah, Zach.
I'm curious, is t our third variable, like a z, like the third variable, or is t like a fourth, like just time, and then the third one we're kind of like ignoring?
So for us right now, we're in, so another really nice thing about parametric equations is this. So this gets at what you're asking. So if somebody says to you, graph x equals 2, what is the graph of x equals 2?
Straight line.
In 2-dimensional space, I agree. What if you're in 1-dimensional space? Yeah, it's just going to be a point, right? If that's 0, that's 1, that's 2. The graph of a point. If you're in 2-dimensional space, so this is R1. If you're in 2-dimensional space, totally agree. Right? That's the picture of x equals 2 in R2. If you're in R3, it's actually a plane. So in R3, the coordinate system is set up this way, and x equals 2 is right there. But notice that the way you should be thinking of when you graph x equals 2 in R2, it means you want all ordered pairs in R2 that have an x coordinate of 2. So there is no y in this equation, which means y has no restrictions on it, so y can be anything, which is what pulls the point vertically and creates the entire line. Same idea here. If you're in 3-dimensional space, you want all the ordered triples that have an x coordinate of 2, so there's no restriction on the y or the z, and if you pull it in the y direction, pull it in the z direction, you're going to end up with a plane that goes on forever, in vertically up and then sideways. So so when you look at an equation in Cartesian, you need more information. You don't know what we call it the ambient space. What is the ambient space? What is the space that this equation lives in? If it lives in R1, that's the graph. If it lives in R2, that's the graph. And if it lives in R3, that's the graph. With parametric, it's really nice because you know the ambient space depending on the number of coordinates here. So if we're in 3-dimensional space, we would have an x equals function of t, y equals function of t, and z equals function of t. So that's going to tell us that we have a curve in 3-dimensional space if we have an x, y, and z, and they're each functions of t. Now, if we wanted to graph a surface in 3-dimensional space, that's also obvious in parametric because there would be 2 independent variables. So here we have 1 independent variable. X depends on just t. Y depends on just t. If there's only 1 independent variable, you are dealing with a curve. Could be in 2 space, could be in 3 space, could be in 4 space, which we can't visualize. If we had a surface, the first dimension, the first space that makes sense to talk about surfaces is in R3. So a surface in R3 is going to have an x, a y, and a z, but you would have two parameters, like an s and a t. X equals some function of s and t, y equals some function of s and t, z equals some function of s and t. No. So that kind of gets at what you're talking about. So the t, the parameters, like we saw with the trigonometric curves, they often have a really specific meaning, like it was representing the angle or some rotated angle of some sort. When we are dealing with, let's deal with this one, which is a little bit different. So this one becomes a little more obvious. We have no trig function. This one's more sort of traditional system. If x is equal to t, then we can replace this t with x. So it's kind of that elimination method that you learned in algebra. So this would be our Cartesian curve. And because this top equation says x equals t, your geometric interpretation of t is that it's equal to it's the x value. So it's not an angle in this case. It's the actual x value. So here is our parametric curve. Now let's do what we did before. Let's get some points here. This has a domain of -2 to 2. So we're going to do t, x, and y. Definitely want to go -2 to 2. -2 and 2, we need those. And you don't have to use the midpoint, but I'm going to use the midpoint. So plug in, OK, t and x are the same, so these ones are easy. And then y is just x squared, so this is 404. So pretty obvious here. When t is -2, we're right there. So that's t equals -2. When t equals 0, we're right here. And when t equals 2, we're up here. So the parametric curve is this portion of the parabola right there. And the orientation is that we're going, we can't really use clockwise, counterclockwise words, but we're going from left to right. Counterclockwise-ish. So that'll be our curve. So our parametric curve is a subset of the Cartesian curve. So let's look at this one. We end up with, pretty obvious, right, that we have the same Cartesian curve. X squared is now x, t squared is now x, so we can replace t squared down here with x, so we're going to have x times x, which is x squared. Now we want to set up our table, so we'll go t, x, and y. And, all right, when t is -2, okay, t is -2, we plug it in up here, we're going to get 4, 16, bless you, 0, 0. And then when we plug in this 2, don't we get the same point, 4, 16? So when t is -2, we're at 4, 16. And then when t is equal to 0, we're down here. But then when t is equal to 2, we're back up here again. So this parametric curve is coming down, hitting the origin, and then turning around and going back. So when we look at this parametric curve, if we were to do an integration once we get to it from -2 to 2, we would actually be getting twice the arc length that we see. So if the question said find the arc length, we would want to go from -2 to 0, or possibly 0 to 2, if we were asked to find the arc length of what we see. So this curve has a cusp right here that we cannot see on this domain. -2 to 2, this curve is not differentiable because there's this cusp that's hidden here where it turns around. So it's equivalent to like an absolute value function where you've got that vertex, the sharp vertex. So this we cannot say, this has no orientation. This is not orientable as it sits with this domain. If the domain was -2 to 0, the orientation would be down. If the domain was 0 to +2, the orientation would be up. So we can't draw an orientation here because it has both those pieces built into it. Okay, so here's another one. When we aren't dealing with trig functions and we're not going to the Pythagorean theorem, we treat it in a much more college algebra way, like it's just a system of equations. We want to use the elimination method. And it's always best to eliminate from the simplest equation, the equation that has no even powers. Right? So this second equation, I can identify t. There's no plus or minus. There's no funny business. If you have an even power and you tried to solve for t, you'd end up with plus or minus the square root of x minus 2 that you'd rather avoid. And that can introduce extraneous solutions. So we want to go with the simplest equation. And then this is going to allow us to write x is equal to t squared. So we're going to get y squared over 16 plus 2. So that is our Cartesian curve. So we can think of this as 1/16 scaling it. So we know that for a parabola, if you multiply by a number bigger than 1, if it's vertical, it gets steeper. Same idea horizontal. If the number was bigger than 1, it would get narrower and kind of steeper in the sideways direction. And if it's less than 1, it flattens it out. So that's why we have this sort of flattened out parabola. And then this plus 2, if it was a y equals over here, that would lift it vertically. But if it's an x equals on the left, then it's going to move it to the right. If it's a positive addition, it would move it left if it was a subtraction. So there is our Cartesian curve. Now we need to go and figure out our location where we are. So we're going to do our t, x, and y. We need the endpoints of our domain, and for good measure. Now, we don't actually have to do a third point when we don't have a closed curve. If we just do -2 and 2, let's just do those two first, and let's just notice something. So we plug in -2 here, we get 6 for x. -2 here, we get -8 for y. So 6, -8, here's where we are when t is equal to -2. And if we plug in +2, we're going to get 6, 8. So with this curve right here, we know that we are going this direction, that direction. We know we're going that way, and we know the curve is going to be that. So we don't need that midpoint. We only need it if it's a closed curve, so we can tell clockwise or counterclockwise. But in practice, it's always helpful to get a third point in the middle just because. So we're at 2, 0, and that would be t equals 0. So we have this parametric curve. It's orientable because the t's are increasing and taking us in this direction. And we get that portion of a parabola. So parametric curves, we can grab, one of the most important things is that you can grab a piece of a Cartesian curve really easily by just restricting t.
So that other one wasn't orientable because it doubled back?
Yes. Yeah, so part of the domain, it was coming down the parabola, and part of the domain, it was going up. So, yeah, and with that other one, we also saw that we had two equations that had the same the same Cartesian curve. So we're seeing, quite frequently now that just because we see the Cartesian curve doesn't mean that's the whole parametric curve. So it depends on the setup. You can have a whole bunch of parametric curves that have the same Cartesian curve. Okay, why don't you guys try this one? So first do step 1, eliminate the parameter t. So that's step 1, eliminate t. I'll let you choose. Which one do you want? Okay, good choice. Good choice. Anyone know what our Cartesian curve is? Not that.
No?
X squared plus y squared is 3.
Yes. So we got to be careful here. So when we isolate sine, do we see sine as y divided by 3? If you isolate sine in the second equation, if you divide by 3, you get y over 3. Has everyone seen that? And then what would cosine be? X over 3? Right, if we look at that first equation, if we isolate cosine, cosine would be x over 3. You see it? So that's going to be what's here, x over 3. And then when we square this, we're going to see that we get a circle of radius 3. We're going to get y squared over 9 plus x squared over 9 equals 1. And so if we rearrange it just because we like alphabetical order, this is our Cartesian equation. So circle of radius 3. So what we're going to see, and you probably can extrapolate at this point, what kind of circle would we get if these were both 5s? Circle of radius
25.
5. And if those are both 10, circle of radius 10, whatever that coefficient, if they match, what do you think might happen if these coefficients don't match?
Get like an ellipse.
You get an ellipse. Exactly. So if we had a 3 here and a 6 there, we'd get an ellipse. Or as long as if those two are both, if they're both those coefficients, if they are different, then you're going to get an ellipse. If they match, you're going to get a circle. Let's actually take a look at Desmos for 1 second. So Desmos can be our friend with these parametric curves. So let's take that off. So if we come down here, so this is how you do parametric equations in Desmos. You just put it, like in parentheses. So that's going to be circle of radius 3, and if we, I didn't put an a in there. Let's make this 0 to 2 pi, and we'll get the whole circle. So we change that to a 2. We get an ellipse. If we put a negative in front of it, we get the same ellipse. Put a negative over here, doesn't matter. If we, sometimes putting a negative will matter, obviously, but here it doesn't because we're squaring it when we do the Pythagorean theorem. So you will get ellipses if those things are not the same, if those coefficients are not equal. All right, in terms of the plotting the points, this goes 0 to pi over 2. So where are you when t is 0?
3, 0.
So we're at 3, 0. Does everyone agree? So this models the very first example we did, which is the typical circle centered at the origin parametrization. We started on the right-hand side. This is going to be t equals 0. A lot of times you can do some of this in your head, a lot of it. As you get more and more comfortable at generating intuition for parametric graphs, parametric curves, and then pi over 2, where is that going to be? Up here, 0, 3. If you plug in pi over 2, cosine of pi over 2 is 0. 0 times 3 is 0, so x is 0. Plug it in there, y is going to be 3 times 1. So this is our parametric curve. And we'll put an arrow in the middle. So that's our parametric curve with its orientation, counterclockwise. Yeah, so super easy. Just sort of think about when you're eliminating the t, you want to isolate sine by dividing, isolate cosine by dividing, and then doing a direct substitution. All right, so try this one. Try this one. I'll draw a picture See if you can figure out which parameterization would do what this is asking. We want to start on top at 0, 10. And we want to go clockwise. Well, if you look back, I mean, the issue here is that you're going to shift, your center is not going to be the origin anymore because you've shifted your x coordinate.
That makes sense.
Right. So if you look at the parameterizations that we did initially with that first unit circle, we had cosine and sine, and then we had cosine of negative t, sine of negative t, then we had sine of t, cosine of t. One of them did start at the North Pole. So one thing to think about is that the standard parameterization starts at 1, 0. Right, so cosine is 1 and sine is 0. And we want to sort of switch that so that we'd be at the top. Instead of 1, 0, 0, 1, or 10, 0, 0, 10. So if we want to switch, so what do you think we should do with this? Let's just talk about the sine and the cosine and the start point. So if we look at the typical parameterization of the unit circle, it's cosine and sine. And if we have cosine and sine, that starts us over here. So if we had cosine and sine and we just had a unit circle, that would put us here, 1, 0. If we switch cosine and sine, that would put us at 0, 1. So this is going to put us, instead of doing cosine first, this is going to put us at the top instead of at the right. Right? Because we're swapping the meaning of cosine and sine. And then if we want a radius of 10, what do you think we're going to do? Multiply by 10. Yeah, whatever that coefficient number is, if both are the same, that's going to give us a circle of that radius. Yeah?
Would it not be root 10?
It would not be root 10. We'll see why in 1 second. So then the domain 0 to 2 pi. So if we want one circle, we'll go 0 to 2 pi, include the 0 but not the 2 pi. If you include the 2 pi, you've done a circle plus 1 extra point. So we'll put a, and some of these books are very sloppy with that. Sometimes they'll just put greater than or equal, less than or equal to them both. Technically, if you want the circle, that's what it should be. Now it's not going to matter if you were trying to find arc length and you integrated 0 to 2 pi, whether you include it or don't include it, you're going to get the same arc length. But technically, it's better to put that. So now, Corbin's question, we sort of saw this on the last one, but let's just illustrate it again. If we were to solve for sine, we would have this. And if we were to solve for cosine, we would have that. And then our identity says that sine squared of t plus cosine squared of t is equal to 1. So if we square sine, we're going to get x squared over 100 plus y squared over 100 equals 1. And so then when we multiply both sides by 100, we will get a circle of radius 10. Right, because x squared plus y squared equals r squared is the equation of the circle centered at the origin. So the radius of this is in fact 10. So that would be our Cartesian curve. And that would be what we're looking for. Make sense, Corbin? Yeah. All right, let's take our break. And then I'll check in with Corbin. Let's take 10. Let's see. So let's talk about lines. Lines, mathematical lines. So the important features of a line are a point on the line and the slope of the line. So we need to translate that over to parametric form, and this is what the parametric form of a line looks like. And we could easily verify that this is true by solving one of the equations for t and plugging it into the other, and you'll get the point slope formula. Point slope formula, y minus y0 equals slope times x minus x0. So if you solve the top one for t and plug it in down here, you'll get the point slope formula. So when we look at this, let's notice a couple of things. So slope b over a, those are going to be these coefficients of t. B over a, that's going to give us the slope. And the x naught, y naught is the sort of origin of the line. That's how we usually think of it. So it's a point on the line. And if a is 0 and b is not 0, you have a vertical line. So if a is 0, then this coordinate is just x equals x sub 0. So you're vertical. And the y's are whatever these generate from the y equation. So otherwise, you have a non-vertical line as long as a is not 0. So let's take a look at this one right here. So we need to be able to identify the initial point, the origin of this parametric line. And when we look at this, both of these are linear, which will correspond to a line, but you still can get a line even if those aren't linear. Like in rectangular, y equals mx plus b or ax plus by equals c. There's no other way to get a line with squares. If you square the x or you square the y, you're not going to get a line. But here you can do parametric, you can do some funny things and still get a line, even though it might not look linear. So what is x naught and y naught? Those are the initial values for x and y. You just plug in t equals 0 into both of those, and you will get 0, comma, negative 4. So that is the initial point on the line. B over A, we take the coefficients of t. So this b over a, the slope, we essentially are taking the two slopes from the parametric equations and forming one slope. So we take the y slope and put it over the x slope. That's going to give us the slope of our line, so 3 divided by 2. And then the xy equation. We know how to do it from this point, with the point and the slope. We're going to do y minus 4. This is point slope. Equals the slope multiplied by x minus x sub 0. So if we wrote this, we simplify this a little bit. Generally, we're going to solve for y. Lines in two-dimensional space are functions unless they're vertical, so usually we'll solve for y. So we're going to have 3 halves x. 3 halves times 0 is 0, and then we're going to subtract the 4 to the right. This will be the line in slope-intercept form. Now, if the question said put it in general form, you would put all the x's and the y's on one side, and usually try to get rid of your fractions. So if we multiplied by 2, I claim that the line would be 3x. So I'm going to multiply everything by 2, and I'm going to move the y's to the right. And then I'm going to move the 4 to the left. So this, I claim, is the general form of that line. If I did my addition well, multiply by 2 and, oh, how did that 4 not turn into an 8? So that. So if it asks for the equation of a line, slope-intercept form's usually totally fine, but if they wanted it in general form, you usually write it ax plus by equals c, and you usually get rid of fractions. That would be the standard form of the general equation. Now, if you've had vectors, and you've studied vectors a little bit, you can do this with a vector approach also. It's not necessary, but you can. And so the two slopes from the x and y equation, you can form this vector a comma b, and we would call that a direction vector for the line. Let me just show you this picture. So there is a rule with vectors that says if you were to add two vectors and you position them like this, if you have two vectors, vector is just a directed line segment, then the sum of them is going to be this diagonal right here. This would be R0 plus V. Now, if you haven't had vectors and you don't want to deal with vectors, you can just sort of zone out for the next 2 minutes. Maybe you do that anyway, I don't know. Doesn't matter. So that's how vectors work. We would call the AB vector, that's the one in red here. These are the two slopes from those two individual parametric equations. That sort of is the direction vector for the line. It just points in the direction of the line. It's kind of like slope. It's analogous to slope. R sub 0 is this blue dotted vector that points to the initial point on the line. And then the idea with this t right here, here is the vector equation of the line. You start at R sub 0, and then t tells you how far to go in the v direction. If you put a 1 in for t, you would be right there. If you put like in a 2 for t, you would be right there. A 3, you would be right there. A -1, you would be over here. So this t is going to take you up and down from that direction vector and create the entire line. So if you're into vectors, you can think of it that way. If you're not into vectors, it won't be long before you have to get into vectors. Once you get into Calc 3, you do tons of vectors in physics 2. Okay, so we've got this parametric line right there. Those are the parametric equations. What is x naught, y naught in this case? One negative 1. So we take the t value of 0, plug it into both places, plug in t equals 0. So it's just the constants, right? It's the x constant and the y constant. So 1 comma 0. 1 comma -1. Plug it in 0. B over a. So that takes, so we're trying to find the slope of our line. We take the two individual slopes, and we're going to form a fraction, b over a. So 2 divided by -1. So 2 over -1, so the slope is -2. So the xy equation, point slope formula, y minus minus 1 equals slope times x minus 1. So there's our point slope form. Y equals mx plus b is totally fine. So we've got -2x. This is going to be a positive 2 when we distribute the slope, but then we have to subtract 1, so we're going to end up plus 1. That is our slope-intercept form of the line. All right, so let's make it a little more complicated. notice that we haven't had any restriction on t. So we're getting the entire line, both directions. So let's chop it up a little. Let's add a restriction on t to get a line segment. So if you're going to do it with a vector approach, if you're going to think in terms of vectors, that would be the equation. It's always going to be from 0 to 1 to get a line segment if you create your direction vector by taking the terminal point and subtracting off the initial point. So this direction vector for a line segment, we're going to form x1 minus x0 and y1 minus y0. That's going to create that vector v that directs the line. And so it's basically taking up the entire segment. If you do terminal point minus initial point, your direction vector is the entire segment, so it's going to be t equals 0 to t equals 1. But if this is your segment you wanted, and you have a scaled down direction vector, your t value might go from 0 to 4 or something. So it kind of depends. If you're thinking about a line segment, the most natural way is to do terminal minus initial and then do an interval of 0 to 1. But you could have a different interval. So let's start here. So drawing a picture is not a bad idea here. Whenever we're trying to, if we have any trouble visualizing something, draw a graph. That always helps. So there's -1, 0 where we want to start, and we're going to finish at 2, 5. So this is the line segment, and we want to be going this direction. So x naught, y naught, that's our start point. X naught, y naught is where we're starting. So if we want to build a line segment, we want to start at -1, 0. This is our x naught, y naught. The start point is x naught, y naught. So that's -1, 0. Now let's form the slope. So the slope is connected to this direction vector thing. This direction vector thing, change in y, change in x, and slope, of course, is change in y divided by change in x. So we're going to form that here. So this is going from terminal. This terminal point is there, initial point is here. So the y's are going to be 5 minus 0 in the numerator. The x's are going to be 2 minus 1 in the denominator. So this is forming the slope, which will be 5/3. And of course, that should match over here. This is -1. That's 2. And this is up here at 5. So the slope is up 5/3. Up 5/3, change in y over change in x. The direction vector, we would say, is 3, 5. All right, so the vector 3, 5, what that means is that we start here and we come over 3 and then up 5. So that would be the direction vector if we're taking a vector approach. All right, so let's write these parametric equations down. So x is going to be, and I've written them up here. So x is going to be x sub 0. And y is going to start with y sub 0. And then we have t multiplied by the change in x or the change in y. So the change in x is -1. All right, so down here, 3. The change in x is right there, 3, x1 minus x0, change in x. And the change in y is 5. So our parametric equations will be x equals -1 plus 3t, and y will be 0 plus 5t. And the t will go 0 to 1. Let's write it this way. And here we want to include both endpoints. So let's check. When you plug in t equals 0, you're at -1, 0 right there. T equals 0. So that checks. When you plug in t equals 1, you're at 2, 5, which is right here. So that'll be our domain for these parametric curves. So those are what they look like in their worst looking form. But all it is the initial point, and you add the change in x times t and the change in y times t. That's it. And we've seen already that change in y over change in x is our slope. Right? That's the change in y, that's the change in x, so the slope goes there, and we have our parametric equations. All right, so you all try this one. So let's leave that one on the board. So try this one. See if you can find the parametric equations for that segment. Remember, you need a domain. No domain means you get the whole line. We want a restricted line. What's x naught, y naught going to be? So it's just that first point, -2, -3. That's going to be x naught, y naught. It's where we start. -2, -3. Slope. Change in y over change in x. -6 minus -3 is -6 plus 3, so -3. Change in x, 6. Everyone okay with that? So we could reduce that. We've got to be a little careful though. So let's watch what happens. Our instinct is to reduce it, of course, right? Right, the slope is -1/2. So now let's do two different things here. So x is going to be the starting x value, which is -2. The y is going to be the starting y value, which is -3. And then we add t multiplied by the change in x. So initial x plus change in x times t. The change in x kind of depends on where we look here. If we want to be super, kind of original, we're going to say, oh, the change in x here is 6. And then the change in y is -3. And we would have the equation -2 plus 6t. And then the y equation would be -3 minus 3t. And let's check our interval. Is that true? So let's draw a little picture. We're starting at -2, -3. We don't have to get very precise, but somewhere down here. And then we're going to end at 4, -6, so somewhere down here. Let's check. When we plug in 0, we're at -2, -3. And when we plug in 1, we would be at 4 comma negative 6. So yes, that gives it to us. Now, if we did this simplification here, we've got to be a little bit careful. We would want to think of that negative as being in the numerator and the 2 being down here. And if we did it that way, notice this difference. So we're going to do x plus the change in x. So x is negative 2. Change in x is negative 1 multiplied by t. For y, the initial y is negative 3. Plus the change in y, we're going to treat that as the change in y. And when we plug in our domain, let's see, if we plug in 0, okay, good. We're at negative 2, negative 3. Right, that's this point right here, negative 2, negative 3. And this point is 4 comma negative 6. When we plug in 1, are we at 4 comma negative 6? No. What did we divide top and bottom here by? 3. What happens if we plug in a 3 here? Where are we when t is 3? Did that even put us there? No.
Yeah, I was about to say, didn't you swap the just x and y? I think the y equation was supposed to be minus t. And then
Did I swap them?
Yeah.
Let me think.
I think so.
So this should be x is in the bottom.
It would be negative 2 plus 2t, right?
Yes. Yeah, I put the x's with the y's and the y's with the x's. Y's go on top, so this should be negative t there. Now let's check it. Okay, sorry about that. So x's with x's. Change in x is down here, change in y is up there. So if we plug in 3 here, we get 5 minus, what's 2 times 3? 6. We get 6 minus 2, which is 4. And if we plug in a 3 here, we get negative 3 minus 3, which is negative 6. So this would be an alternative domain here if we did a reduction in the slope formula. So we just have to be careful. If we use the original change in y over change in x, it's always going to be 0 to 1. But if we do a reduction, we've got it. This is going to be our x's in the bottom, y's in the top, and we have to modify the domain by whatever we divided out. So we sort of took the direction vector and shrunk it by a factor of 3. So we have to increase the domain by a factor of 3 and go from 0 to 3 instead of 0 to 1. It's easiest if you just go 0 to 1 and you don't simplify. That's going to be easiest. Then you're always 0 to 1. Okay, so we've got these parametric curves floating around in 2-dimensional space, possibly 3-dimensional space if we're thinking about Calc 3. The first question in calculus we always ask is the rate of change. What's the derivative? What's the slope of the tangent? And with parametric curves, it's pretty straightforward. If we have our parametric curve, so we have x as a function of t, y as a function of t, to find the derivative, to find dy dx, to find the slope of the tangent, we do g prime over f prime. That will be the slope of the tangent at a particular t value. And of course, we can't divide by 0, so f prime of t can't be 0. So not too crazy. Y over x. Now y and x are both functions of t, so we do dy dt and dx dt. So here are some parametric curves. All right, we've got our x, we've got our y. So the derivative, which we still represent, dy dx, that is going to be y prime of t divided by x prime of t. So this is interesting because traditionally, when you have dy dx, you are trying to write the derivative as a function of x. And you think of x as the independent variable. But with parametric, x is not the independent variable, t is the independent variable. So y prime of t is going to be 8 cosine of t. X in the denominator, take its derivative, we get minus sine of t. We could write this as minus 8 cotangent of t. Cosine divided by sine is cotangent. So the derivative is now a function of t. Now it says, find the value of the derivative at t equals pi over 2. And here's how we are going to notate this. So we're going to put a vertical line and put a t right down here to indicate that we're evaluating. We're not just going to put parentheses of pi over 2, because if you just put parentheses, that would imply it was an x value. So we're going to do this little new notation thing, and then all we have to do is that. Let's think about the unit circle for a second. We don't think about cotangent a ton, so let's just draw a picture, make sure we're on track. So pi over 2 is right there. This point is 1, 0. What is cotangent of pi over 2? Zero. Right? Good boy. Right? Tangent is y over x. Tangent is slope. So tangent is undefined here. 1 divided by 0, tangent. Cotangent is the reverse, the reciprocal. So it's x divided by y. 0 divided by 1 is 0. Yeah, good. So it's negative 8 times 0. So so what does that mean geometrically? If we have a derivative that's equal to 0. Derivative equal to 0?
It's a constant.
So the derivative is, what does the derivative represent geometrically?
It's a line.
It's going to be, it's the slope of the tangent line, but the tangent line would have to be horizontal. If the derivative has a value of 0, it means that on the curve at pi over 2, we must have a horizontal tangent line. So if we were to graph this, what do you think the graph of this is going to be? We have a sine and a cosine, but different coefficients. It's going to be an ellipse. It's going to be an ellipse. Let's graph it real quick, since we're pros at this now. We're pros at graphing, yay. What is sine equal to in this? Sine is, if you isolate sine,
y squared over 64.
y over 8, right? So y squared over 64. And cosine is already isolated to be x, so this is our ellipse equation. Do you remember how to graph ellipses? So if we're graphing that ellipse, the center is 0, 0, because it's y and x. It's not y minus something and x minus something. There's no parentheses, so the origin is the center. And you go from the center, you look under the y's, and you take the square root, and you get 8. So that means you're going to go up and down 8 in the y direction. That's two, I don't want to draw 8 tick marks. So this is up here at 8. This is down here at negative 8. And then you look under the x's and you see a 1. So that says go right and left 1. So we're going to go right and left 1. So here is our ellipse. Let's see. Do I remember how to graph? I don't know. Let's see. If I do that, I will do it. That's pretty good. Not too bad. So there's our ellipse. Now, the place that we are on the ellipse when t is pi over 2. Plug in pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. 1 times 8 is 8. So we are right here. Let's see if I can shrink that a tiny bit. So we are right at the exact top, correct? So we are right here when t is equal to pi over 2, right? Because we plug in pi over 2, and we get 0, 8. So that's the location on the parametric curve at pi over 2. And we just saw that the slope of the tangent at pi over 2 is 0, so we have to have a horizontal tangent line there. What do you think if we plug in t equals 0? If we plug in t equals 0, we'd be at 1, 0. We're right here. What do you think the slope's going to be there? Undefined. Right? So if we came down here, let's look at this form. It's a little easier here. If you plug in 0, cosine of 0 is 1. You'd have 8 divided by 0, which is undefined. Okay, so similarly, if you plug in pi is going to pop us here. You're going to get undefined there. And 3 pi over 2 is going to give you 0 also. So that's how it's going to correspond to the graph. Let's take a peek at this one. So here we've got parametric curve. We haven't graphed it, but we see it. We know it's a parametric curve. We have an x, a y. So if we were to graph it, we could. Don't need to, though. dy dx is going to be 3t squared divided by 2. So that's the derivative. You take the y derivative, put it over the x derivative. That's your parametric derivative. And they say, well, what's the derivative at t equals -1? So then we take our derivative notation and we modify it with this little evaluation symbol. And all we do is plug in the -1 for t. And we're going to get the slope of the tangent at t equals -1 is going to be 3/2. So if we wanted a visual, we would graph this parametric curve. We would identify the location of the point on the curve by plugging in a -1 here, and you can see that it's -2, -1. So at that position on the curve, the slope's going to be 3/2. The tangent line would have a slope of 3/2. So not too different than when we're dealing with Cartesian. So parametric curve. There's our parametric curve. So it says find the equation of the tangent line to the curve at the point corresponding to t equals 2. So let's first notice where we are when t is 2 on the curve. So this is a tough graph. You would never have to graph something this complicated by hand. But if you plug in a 2 here, we are at 3 for x and 10. So 3, 10. So this is corresponding to t equals 2. That is where we are on the parametric curve when t is 2. That's our location. Now we want to find the slope, the equation of the tangent line. Well, we know how to do that, but first we have to find the slope of the tangent line. So dy dx, derivative of y is 3t squared plus 1. Derivative of x is 2t. So there is the slope of the tangent line. We want the slope of the tangent line at 2. So we're going to do the slope of the tangent line at 2 by substituting a 2 in here. So we get 13/4. Okay, so let's just write this. It doesn't actually say whether we should write the tangent line in parametric form or rectangular form. Let's do it in rectangular form. So y minus what? Point slope formula. Y minus 10. We're drawing the tangent line at this point. So y minus 10 is going to be the slope, which we just found, to be 13/4 times x minus So point slope formula. And normally we would isolate y if we're writing it in rectangular, so we would write this as 13/4 x. And then we would distribute this and we'd get minus 39/4. But then we would add 10. So our simplified slope-intercept form would be 13/4 multiplied by x. Here we'll write that as 40/4, so plus a fourth. That would be our tangent line. And then our tangent line will be, going right through that point, roughly there. Let's try another one. So, what is dy dx here? Tell me what dy is. Tell me the numerator first.
1/2t+1.
Yeah, 1/t + 1. So we're taking the derivative of a log function. Derivative of log is 1 over the inside, multiplied by the derivative of the inside, but the derivative of the inside here is just 1. And then we divide by derivative of the x equation, derivative of e to the x, e to the x, or e to the t, letter is t. And if we simplify this, we'd have 1 divided by e to the t multiplied by t + 1. You can treat this e to the t as an e to the t over 1 multiplied by the reciprocal. So we look at our curve. We didn't graph this. This graph's given to us right now. But we can figure out where we are in the graph when t is 0. If we plug in t equals 0, we are going to be at, plug in a 0 for this, x coordinate, e to the 0 is 1. Plug in a 0 here, we get natural log of 1, which is 0. So this is where we are when t equals 0. And the tangent line is going to look sort of like that. Okay, so to find the equation of that tangent line, we need to know the slope at that t value. So we want dy dx evaluated at t equals 0. So we come into this derivative equation, plug in a t equals 0, and what do we get as our slope?
1.
1. Plugging in 0 for all the t's that we see. E to the 0 is 1. So then we do our point slope formula. Y minus 0 equals the slope multiplied by x minus 1. And this gives us y equals x minus 1. So there is our tangent line. So slope is 1, y-intercept is -1. So my line is a tiny bit skewed. I should rotate it just a skosh. So it looks like it's going to go right through -1. Make sense? So kind of back to what we did in Calc 1, we're just doing it with derivatives. Another Calc 1 thing we did, actually we've done it in this class, arc length. So the arc length formula that you're familiar with, the one that we used a lot, looks a little bit different. We had the square root of 1 plus y prime squared dx from a to b. Looks very similar, it's just that instead of the 1, we have an x prime squared and a y prime squared. And it's coming from this same picture that we used back when we developed that formula. It's just that instead of manipulating the square root to figure out this length here, the ds length, instead of forcing it to be a dx or a dy on the outside, we force it to be a dt on the outside, and we get the ds is this function of t times dt. So we use the same logic that we used back when we did arc length originally. Pythagorean theorem, take the square root of both sides, and that's what we get. So let's try this one. So there is our new formula for arc length of a parametric curve. We have a parametric curve right here, x and y. So arc length, notice that our limits of integration are now t limits, not x limits or y limits. And the setup for arc length, we're going to integrate on the interval 0 to t, 0 to 2. And then all we have to do is find the derivative of each of our coordinate functions and then square them. So what is x prime squared? 9. And y prime squared? 16. So we're going to get the derivative squared plus the derivative squared dt. So this integral will go 0 to 2. Oh, 9 plus 16 is 25. Square root of 25 is that. So this is 5 multiplied by the integral from 0 to 2 of dt, which is 10. Because the integral 0 to 2 of a differential is the length of the interval. So integral 0 to 2 of dt is just 2. When you integrate a differential, the result is the length of the interval. So that is our arc length. That is our arc length. Pythagorean theorem. Let's try another one of those arc lengths. So sometimes it's helpful to write these parametric curves kind of in system notation. So I'm going to rewrite this in system notation. And what you should be recognizing here is that this is a circle that's shifted because we added 1 to one of the coordinate functions. So that's going to be a shifted center. We shifted the y up 1. So the x is still at 0. The center of the x part is 0. Center of the y part is 1. So it's 0, 1 for the center of the circle. And if we want to find arc length here, aka circumference, sometimes it's helpful to do this system notation. Keeps it a little bit neat. So we just take the system of equations for the curve, and then we form the system of equations of derivatives. So this is going to be minus 3 sine of t. And then this derivative is 3 cosine of t. And then our arc length, we're told that we want the circumference of the circle. We want to go from 0 to 2 pi. And so here's one of these places where sometimes they're a little sloppy, and they include or exclude the 2 pi. Technically, if we want just the circle and not the circle plus a point, we should have a less than or not a less than or equal to, just a less than. But it doesn't matter when we're integrating. So, so it's totally fine. The integral, whether we include or exclude the 2 pi, is the same, because we would put a 2 pi there. So now we do the square root of x prime squared. So that's going to be 9 sine squared of t. And y prime squared is 9 cosine squared of t. And what does the inside of this simplify to? That simplifies to square root of 9. Right, if we factor out the 9, we get sine squared plus cosine squared, which is 1. So inside the square root, we factor out the 9, and we have sine squared plus cosine squared, which is 1. So we're left with just square root of 9. So can you see what this overall value is going to be?
6 pi.
6 pi. Right, the length of the interval is 2 pi. Square root of 9 is 3, so we have 3 multiplied by 2 pi. So we get 6 pi. Does that make sense? What is the radius of this circle?
3.
3. Perimeter of a circle, circumference is 2 pi r, so 2 pi multiplied by 3 would be 6 pi also. So it matches what we think. All right, let's take a look at this ugly looking thing. So this is a circle centered at the origin. It's not obvious that these parametric equations give us this circle. It's not even, so it's not obvious it's a circle to us. We see these parametric equations, we type it into Desmos and graph it. Trying to eliminate t here would be kind of a feat. It's possible though. You could do it. But we don't need to do it. So let's treat this blindly. We'll just say, okay, well, we have x. We don't know if it's a circle or not. It's not obvious that it's a circle. So we can just do arc length. To do arc length, we're going to form the system of derivatives. So we're going to take the derivative of the x equation. We're going to get negative sine of t minus cosine of t. We're going to take the derivative of the y equation. And then we have to square them both. And before I put them inside the square root, maybe I'll just square them here because we're going to see some simplification that will help. So if we've got to square that, we need to FOIL with negative signs. Okay, so foiling this, we're going to get sine squared. And I agree that at the end, we're going to get cosine squared over here, positive cosine squared. So those are the easiest two terms. And then to get the middle term, you multiply the a times the b and double it. Right? Everyone agree? A times b and double it. So a times b is going to be sine times cosine. And we double it, and we get 2 sine times cosine. Foil. If you wanted to, if you hate this minus sign, you could factor it out. And when you square, the minus would go away. And you square negative 1, it becomes positive 1, and then you square this, and it becomes sine squared plus cosine squared, and then 2 sine cosine. So you could do that if that makes it more copacetic. Now, doesn't this simplify into 1 plus 2 sine cosine? Right? Okay, y prime squared, we're going to get sine squared. And the last is going to be cosine squared. The middle, a times b doubled. So negative sine times cosine doubled is negative 2 sine cosine. So this is all going to simplify to 1 minus 2 sine t cosine t. Now let's go to the arc length formula. L equals the integral. We're going 0 to pi here. Square root of x squared, x prime squared plus y prime squared dt. And what happens when we add these two squares together? We get the square root of.
It doesn't waste the battery.
I did bring this messed up. They said it was.
Did someone say?
Yeah, 2.
2? Let's see. When we add those together, we get 2. Yeah, great. That's easy. What's the final answer? Yeah, square root of 2 times pi. Square root of 2 times pi. Now let's look and see. If this is really a circle, what is the radius of this circle? What's that distance?
1.2.
Square root of 2? Everybody agree? Right, because we're at 1, 1. The diagonal across 1, 1 to the origin is going to be root 2. And if we were going to find the arc length of the full circle, it would be 2 pi r, but we only want half a circle, so it's pi r, so it's square root of 2 times pi. So it is, in fact, a circle. Turns out that it's a circle after all. So a good exercise, if you're feeling frisky, is to isolate, turn that into the equation of a circle of radius root 2 centered at the origin. Takes a little bit of work. It's not obvious. All right, let's do something new. Let's do something new. We're tired of parametric equations. Parametric equations. So none of the stuff in chapter 12 is hard, but you definitely have to just give it enough time so that so you can process it. All right. When you get into Calc 3, you're going to see that there are 3 coordinate systems that are very commonly used. And we use different coordinate systems in different cases because of simplicity. Sometimes looking at things through a rectangular coordinate system creates a lot of extra work. And sometimes using another coordinate system makes things simpler. The first coordinate system that we're going to look at that's different than rectangular or Cartesian is called the polar coordinate system. Normally, when we're doing rectangular coordinate systems, we look at that point and we think, oh, that's x comma y. In the polar coordinate system, instead of looking at that point as x comma y, you can think of it as r comma theta. So r comma theta, r measures the distance from the origin, and theta measures your counterclockwise rotation. So you can call this r comma theta instead of x comma y. If we are looking at a point that is down here in quadrant 3, that's opposite this point in quadrant 1, there are multiple ways to represent it. One way to represent it is by putting a negative r value. Now, typically when we think of the r value, we are thinking of positive, right? We're thinking distance to origin. In polar, which is an anomaly, you can have a negative r value, and it shoots you into the opposite quadrant. When you get into Calc 3, you can't have negative r values, but in 2 dimensions, you can have negative r values, and it just shoots you into the opposite quadrant. All right, so we'll talk about that as we get closer to an example. The important thing for us is how do you move back and forth between the 2 coordinate systems? And the answer is this right triangle right there. This right triangle builds these 4 equations that take us back and forth. If you look at cosine of theta is x over r, multiply both sides by r, and you get this equation. Sine of theta is y over r, multiply both sides by r, you get this equation. Pythagorean theorem, tangent of theta is vertical over horizontal. So those 4 equations are the crux. They take us back and forth between the 2 coordinate systems. So one of the weird things in polar is that every point has an infinite number of representations. You can pick different r values and you can pick different angles. We'll talk about this on the next page. So you can have positive thetas, negative thetas, positive r's, negative r's. You can have a whole bunch of stuff. So let's take a look at some options. Let's start with point A. The standard representation is r comma theta. The standard representation for this point A would be to write it as r comma theta. If we look at this polar graph paper, can you see that we're on the radius 2 circle? There's radius 5, radius 4, 3, 2, 1, 0. So r comma theta, if we rotate counterclockwise, this is going to be our standard representation in polar of that point. That's the representation most of us prefer. Positive rotation, positive radius. Here are 3 other representations that we could use. Let's pick a positive r value, but a negative angle. So a negative angle would take us, we would start there and we would go this way for a negative angle. That negative angle would be negative, let's see. These are pi over 6s here, so 1, 2, ooh, gosh, that's hard to count. So negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi over 6, so negative 5 pi over 3. Negative 5 pi over 3. So that would be using a negative angle. Does that make sense? You could also choose negative r values. So if we choose a negative 2 as our r value, we would have to land on this terminal ray for our theta. So our positive theta, that's less than 2 pi, would be right there. And what's that theta?
Pi over 3.
So 4 pi over 3. So that would be that representation. And now if we're hyper-contrarian, we're going to say, hey, man, we want negative and negative. So if we want to get to this green terminal ray coming from the negative, we go this way. So that's going to be negative 2 pi over 3. So if we go negative 2 pi over 3 and we have a negative radial value, we bounce into the opposite quadrant and it puts us back into quadrant 1. So those are the 4 ways that you could represent this point. This is the standard representation here. Positive r value and a theta between 0 and 2 pi. That's, most of us would prefer that. Okay, so that's what we just did here. We just did A. And there's an example B. You can look at B. Let's take a look at point C. So point C is right there. What is the standard representation for point C? What's the R value for point C?
4.
4. And then what is the standard angle counterclockwise rotation from here? We're bisecting quadrant 2. We're going right down the middle of quadrant 2, so that would be 1, 2, 3 pi over 4. 3 pi fourths. That's going to be our standard representation right there. Now let's go positive, but with a negative angle. What would our negative angle be to get there? All the way around. So negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, negative 5 pi over 4. That would take us all the way around. Now let's pop some negative radial values in here. So negative radial value would mean that we need to land on this terminal ray right here. So what is this negative number there? Negative pi over 4. So that will be this super contrarian one. And then the positive option there would be to come all the way around to there, which would be 7 pi over 4. All right, so all those representations are possible. Typically, we like the standard one, but just so you know, you can use any representation imaginable, which makes grading a pain in the neck, because there's lots of correct answers. All right, last problem. Then we'll go. So convert the following polar coordinates to Cartesian. Now these, when you look at them, are pretty obviously polar because you see that radial angle. But it's not, this is just a number, so it could be Cartesian. So I like to put a little p here just to indicate that it's definitely polar, because you could have 1, 1 where the 1 represents 1 radian. So typically it's from the context that you determine if it's polar or Cartesian. But putting a p there is just convenient. So the nice thing is that when you're going over to Cartesian, it's super simple with those top 2 equations. So x is equal to r cosine theta. So r in this case is 1. Theta is right there. So it's going to be 1 times cosine of 2 pi over 3. Cosine of 2 pi over 3 is negative half. So this is going to be negative half. Let's label it on here. So 1, there is our point right here. So 2 pi over 3, 1. And then the y coordinate is going to be r times sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 divided by 2. So there we go. Those are the coordinates in Cartesian. So these points are equal. You could write it as negative 1/2 root 3 over 2. It's a point on the unit circle. Put a c there just to emphasize it's in Cartesian. How about that one let's just do it geometrically here. So 3 pi over 4 is right here. And then if we go into the opposite quadrant, we're down there. What is that point in Cartesian? So we'd be at root 2 over 2, comma root 2 over 2 on the unit circle, but then we have to multiply by 4. So it's going to be 2 root 2, negative 2 root 2. We can double check that one on Thursday just to make sure. But if you do the r cosine theta, your r value, you would do right there. You plug in the r value, plug in the cosine, and you'll get those numbers. All right, let's stop. We've had enough math today. Let's stop. Oh, finish up 12-2 on Thursday and start 12-3. Final sections. I think it's going to be nice out today.
Yeah, the unit circle one.